Tobias. Thank you very much. So it's my really great pleasure to be here. It's my first time to the Bay Area and I'm just having a blast. So I was struck in the talks today at the kind of role reversal that I think has taken place in the past 10 years. So in Adam and Dan's talk, we heard about qubits. And in Benny's talk, we heard about black holes. And in Fernando, he begins with a field. And so there's this sense that, like, the tables have turned, and I'm not quite sure, I'm not completely sure who I think the killer whales are. So my own interest in this stuff all began in 2000 and 2001 when I was completing my PhD with Michael. And I read around widely in the high energy physics literature. It's my early wish to do high energy physics. I never got to do that. But I noticed a paper by Halsey, Larson, and Wilczek about the entropy area law in ground state. And also independently found a paper by Ted Jacobson deriving general relativity from thermodynamics. And I thought, well, wouldn't it be great if, like, space-time was entanglement? But to be honest, I lacked the confidence, and I certainly lacked the technical ability to ever make anything of this fantasy. And so it was like I was so pleased when I saw that Tanner Armstrong managed to take it to some kind of quantitative level. And in particular, it's in talks by many of the EI and PPR that I was really sort of convinced that there's something there. This isn't just a fantasy. It's an amazing observation waiting to be sort of unpicked and discovered. But I couldn't really contribute to this field. To be honest, I'm not a high energy theorist, and one thing I really lack is general relativity. So for me, the story begins here. A bit earlier, I'd heard from Fernando about this result. And here was presented a toy model which could explain it in sort of a language that I could understand, the correspondence, this ADS-CFT correspondence, bulk boundary correspondence. And I've been really obsessed with this paper since it came out. Here's an opportunity for me to maybe say something. And the one question that I've been really obsessed with since learning about this paper is like, well, maybe there is like a CFT on the boundary coming from the holographic code. What is that thing? What is this? What would a CFT corresponding to a holographic quantum error correcting code even look like? And so I've been beavering away these past couple of months trying to make sense of that. And today I want to tell you a little bit about what I found. Now, I guess you're not going to like the answer because it's not a CFT. But there's something really tremendously interesting that turns up at the boundary of the holographic state and in the bulk. And I want to tell you about this stuff. And it connects with all kinds of interesting mathematics that are taking place in the operator algebras community right here and now. So this is sort of active research in a whole other community as well. So I've been sort of up in the hills with the operator algebras for the past year, learning this stuff, and now I want to see if I can communicate a bit of what I've learned. So the outline of my talk is as follows. We're going to start with holographic codes, or in particular, not even holographic codes, we're going to talk about holographic state. And I'm going to take the most trivial possible imaginable holographic state, because even there things are really super interesting. Then I'm going to have to deal with something, namely the continuum limit. It's not sufficient to talk about dynamics, I'll argue, without having already a sense in which you've got a continuum limit taking place at the same time. So I'm going to tell you about how we understand the continuum limit for the holographic state, and I'll propose an answer. Then we're going to talk about dynamics. How do you give some dynamics to a state? Well, we're going to need to talk about what dynamics means in high energy physics. And the position I take is that dynamics really comes from a unitary representation of the conformal group. So we're going to talk about that, and in particular we're going to see that we're not going to get that. This is really, where the holographic state just doesn't have the structure that's compatible with the conformal group. But there's something really remarkable which takes its place, and I really want to tell you about that. So that's the second half of my talk. And then, the ultimate objective is to find a toy ADS-CFT correspondence where we can really, it's extremely bordering on trivial, but because it's so simple, we can ask very, very complicated questions of this toy model and hopefully get some helpful answers, or at least see how it would function as a FOIL theory. All right, holographic states. I had hoped by now that there would have been mention of perfect tensors. There wasn't. I'll do it now just quickly. Because we're going to focus on three-leg tensors. A perfect three-leg tensor has three legs, dimension d. You can think of a perfect tensor as an isometry. Now I've adopted the operator algebras community habit of putting a dollar sign here because this is planar. This dollar sign is equivalent to the labeling legs here, 1, 2, and 3, starting with the dollar sign. And a perfect tensor is none other than an isometry embedded in the plane like that, such that if you contract along every pair of legs like that, it's equivalent to the identity. So there's three possible ways to contract this three-leg tensor against its adjoint. Once that's true, we get to call it a perfect tensor. Now, you might be forgiven for thinking that maybe such things don't exist. Well, I assure you they do. Here's a particularly fascinating example that borders on trivial, but is actually deeply related to map coloring. So this is really a surprising tensor right there. And it's also related, as we'll see, to tensor categories. So this particular tensor has got a very nice property that I'm going to exploit all through the talk. It's rotation invariant, right? Just rotate it, you get exactly the same tensor. Very useful fact. But it's not totally trivial. It doesn't satisfy this kind of F symbol associativity property. So there's something non-trivial buried in this tensor. Now, that's just one example, and I'm going to use that example throughout the talk, so I'm going to drop this dollar sign almost straight away. But there are many more examples that turn up, and I think the simplest one that the category theorists out there will mention are Frobenius algebras, the finite dimensional things like that. They're related to matrix product states. It's boring. Sort of a much more subtle example might be the OPE coefficients. So this is an infinite dimensional example. Also, tensor categories. They give rise to many examples of these tensors here. I mean, although you have to contract everything within the tensor category. My favorite example is SO3 and planar algebras, which is developed by Gordon-Jones to deal with the subfactors and polynomial algebras. Also gives rise to multiple examples of these things. Now, that was just a whirlwind tour of three-leg perfect tensors. Now we're going to get to the holographic state, and to do that, we're going to sort of tessellate a slice of ADS3. And so I'm going to focus on these also pretty damn close to trivial tessellations of the slice of ADS3. So this is a tessellation of the Poincare disk by triangles, by so-called ideal triangles. Look, every vertex of each triangle lies on the boundary. So this is about as trivial a tessellation as you can pull off, a regular tessellation of the Poincare disk. And we're going to have occasion to talk about tessellations with distinguished oriented edge. We want to introduce an origin just like we do in real space. And the way we break the translation invariance is by identifying an edge. And so whenever I say tessellation with DOE-E, I mean that. Just color one edge red and put an arrow on it. Now, we're also going to talk about other tessellations, non-regular ones. So we started with regular ones. Now, we're going to talk about also tessellations where we've been allowed to execute a finite number of flips along quadrilaterals. So you pick out a quadrilateral that you like, and then you flip the edge in there. So tessellations where you've executed a finite number of quadrilaterals, that flips through the edges of quadrilaterals, are also going to be allowed in this talk. Now, the next topic to talk about the holographic state that I need to introduce is what I call a cutoff. What does that mean? Well, it's a region in the Poincare disk defined by a bunch of geodesics from a given tessellation. And it's, that's what it is. Now, cutoffs have a remarkable structure with respect to these tessellations. So you can talk about one cutoff being bigger than another. I think that's very important. And furthermore, that these cutoffs aren't in any sense regular. You can sort of refine them as much as you like in some regions and not in others. So I want to, it's not like the cutoff in managing physics where it's just like the energy, right, or the momentum. Here, I'm thinking about cutoffs as being much more a set of many more things. But at the same time, you lose the total order on cutoffs. You only get a partial order
Sorry, which one are you calling bigger?
Oh, sorry, I didn't say it right. So gamma prime is meant to be this dark red thing here. That's bigger than gamma, which is this guy here.
So it's inside of the picture.
Inside, yeah. And so we're going to define actually bigger right now by pointing out that the set of all these cutoffs is a directed set in the language of maths. The relation that this region A gamma is contained in A gamma prime, well, we can write it as gamma is less than gamma prime. It's a partial order. Very, very nice fact. And secondly, it gives a directed set structure to the set of all cutoffs. For every pair of cutoffs, there's always a bigger one. It's a very useful fact. Now the holographic state, if we finally get there to actually reviewing this construction for this very specific example. So here's the world's simplest holographic state. It's a triangle. And you put in B. There it is. That's the world's simplest holographic state. Now, once you've done that, you think, well, why stop at that particular cutoff given by the triangle? Why not let's just associate a holographic state to any of these cutoffs? And indeed you can. You just stick in a V in place of all the triangles inside the cutoff, contract the legs, and then you've got a state on these legs that pass through the cutoff boundary. So the nice thing I want to observe here is that the holographic state construction doesn't just give you one state, but it gives you many states. It gives you a state for every cutoff that you can draw in the Poincare disk. So, but where do they live, right? So there's a Hilbert space that we can put these holographic states in. It's simply the tensor product. Yep.
The dual diagram to the tessellation is a tree or not?
The dual diagram to the tessellation is a tree.
Yeah.
Yeah.
Numbers,
Are they going to be p-adics in this talk? No p-adics here. But it is a tree. Now, I'm glad you noticed that and pointed it out early because I forgot to put in a slide pointing out this fact. I don't want to disguise the fact that this is down in the air close to trivial. These are trees, but what I want to do is introduce all these definitions for the case of the tree and then promise you and conjecture and argue until you accept that these all generalize to more general tessellations. Okay, these states live in some Hilbert space. What is that Hilbert space? Well, you just take the tensor product over all the legs of C to the D, right? I said that the legs are D-dimensional. And there it is, right? So this is to every cutoff, there is a Hilbert space. And in this Hilbert space, there's a special state, which we call the holographic state. So there's the Hilbert space, just repeated for your convenience, the tensor product over all the edges in a cutoff of C to the D. So the holographic state construction doesn't give us one state, it gives us many states. For every possible cutoff that you can draw, you get a state. But they're all in different Hilbert spaces. How do you compare these things? Well, it turns out that the holographic state construction gives us a canonical way to compare two states with different cutoffs. This is really another lovely piece of maths that we're going to exploit. So the boundary space for a system with a bigger cutoff, well, it's just the tensor product of the CDs on all the legs, easy peasy. But look, it's related. That bigger Hilbert space is related to the one with the smaller cutoff by an isometry, not just any isometry, but like a canonical isometry. You get it by contracting all these V's here and here, the bits that you expose when you reduce the cutoff. And so what I've done is I've blocked it all together and called that isometry T gamma to gamma prime. T is an isometry that takes you from the Hilbert space of the cutoff gamma to the bigger cutoff space gamma prime. So that's what you get from the holographic state construction. Works for any tessellation. This is not tree specific. Every Hilbert space H gamma is embedded in a canonical way into the Hilbert space of a system with a bigger cutoff by an isometry T gamma gamma prime. Now, boom. Okay, so this, in a mathematics conference, I just, I say, well, that's a directed system, we're done with that. So here, but the onus is on me is to explain this definition to you a little bit more. So what we managed to extract from the holographic state prescription is a bunch of states, a bunch of Hilbert spaces, all living inside each other. And physically what we're saying here is that if you have some low cutoff, then there's a way to associate a state of a system with a low cutoff to a system with a higher cutoff. There's a canonical way to raise the cutoff. might call that the normalization group. Now the kinematical space for the holographic state, I'm going to just pull all that data together and put it into a definition. So what is it, this kinematical space? Well, it's determined by a directed set. I've already told you what that is. It's just a set of all the cutoffs. And with boundary Hilbert space for each possible cutoff. And there's this lovely extra data, these are isometries, which tell us how each space lives in the other. It's all this very intricate net web of space, subspaces and inclusions. And these isometries have some nice properties, and they're very, very nice indeed. One is that, well, if you have the same cutoff, then it's the identity. Simple. But if you go from gamma to gamma prime, you raise the cutoff, then you raise it again, well, that's just the same as going from gamma to gamma prime prime. And the remarkable thing is that this gives us this gives us a way to compare states with different cutoffs in a sort of master Hilbert space. And I'm going to introduce to you now this Hilbert space where we can talk about these states with different Hilbert spaces. I pointed out earlier that all these states live in different Hilbert spaces. How can we possibly compare them? Well, with this data we can, right? Because there's this very beautiful equivalence relation on states in this system of Hilbert spaces. This state here, psi gamma, well, we said that that's equivalent, right? Physically equivalent to this state here in a bigger Hilbert space with the larger cutoff. So why don't we define that as an equivalence relation? We say that psi and psi gamma prime are the same if they differ by this t. And now we can build a Hilbert space that contains all of these subspaces in a canonical way. And I mean canonical in the mathematical sense, and I mean it also in the physical sense as well. So what you do is, what's the first thing you might say is, well, okay, let's just take all these boundary Hilbert spaces and take the union. But that's not a Hilbert space. Crap. Okay, so then we take a disjoint union, and then we have to mod out by this equivalence relation. This disjoint union here is just too big, right? There's so many states in there that are just physically indistinguishable in the IR. So we mod out by that equivalence relation here, and then we get a Hilbert space. When we don't, we have to complete with respect to the norm, but don't worry about that. And so in the end, we get a sort of master Hilbert space that contains all these states with a given finite cutoff. Now, in words, what this means, this symbols here, they all mean this in words. So H hat, the semi-continuous limit, is a disjoint union of all these boundary Hilbert spaces over all the cutoffs, modulo the equivalence relation that two states are equivalent if there is some bigger cutoff, bigger than both of these two cutoffs. We know that there always is such a cutoff, such that these two states in that bigger boundary Hilbert space are in fact equal. And then this is a legitimate Hilbert space. It's an infinite dimensional Hilbert space, even though all the other questions. The difference between union and disjoint union, very good question. In the union, if we have two states that are, two elements that are the same, and you take the union, then you don't double up, right? You just sort of take one. So if you had a set 1, 2, 3 and a set 1, 5, 7, then the union is 1, 2, 3, 5, 7. But in the disjoint union, you add a little tag. And so you can have one L, one from the first set, and one R. So the disjoint union. Here we just tag each vector by the space it comes from. So elements of a disjoint union. So if you have something in there, then it's a state, psi gamma, plus a tag, meaning it came from the Hilbert space associated with a cutoff gamma.
So since all the smaller states will be mapped to some states in a bigger region, so why don't I just directly take the bigger one and take the side 2 equal? Why do I need the smaller one?
Because it's only a directed set and not a totally ordered set. So that's a technical question that I might come back to. So this I'm calling this semi-continuous limit and not the continuous limit for a reason, and we'll see that later. So what is it? Well, it's an infinite dimensional Hilbert space and it's separable. So that's a nice thing to have. We don't like inseparable Hilbert spaces, although I sort of don't know why they're so bad. But maybe someone later can explain that to me. Okay, but who lives? What are the residents of this space? And I hope this maybe begins to clarify this distribution. So the residents of H hat are sequences of boundary states for increasing cutoffs such that each of these phi gammas are just the image of some IR state of psi gamma for some gamma. So we know these equivalence classes are huge, right? There's just an infinite sequence of such states because there's always a bigger cutoff. And I would like you to, and I would encourage you to think of the residents of this Hilbert space as just UV completions of some given state with some given finite cutoff. So a picture I'd like to draw for that is you start off with some state within the boundary Hilbert space H gamma defined by some cutoff gamma, and then you UV complete, you embed until you've completely UV completed that state to an element of some Hilbert space. What Hilbert space? Well, none other than this H hat. Now, there's a very special state inside H hat. This is like the holographic state. It's when, if you look under the hood, then you see that that state there was built just from the V's associated with all the triangles of the ideal tessellation. So that's one very special vector inside H hat. Let's call it the vacuum state. Now, you might wonder, how can we actually compare two states inside this infinite dimensional Hilbert space? Well, what you do is you find two representatives of these states. Perhaps they have different cutoffs. So how do we compare them? Well, let's start UV completing until they live inside the same boundary Hilbert space with some cutoff gamma prime. And then, how do you take the inner product? We just do the dagger, right? There we go, just did the dagger. And then you contract. Just like that. And then if you work out what this is in terms of equations, then you get something that's very difficult to parse because of all the brackets. But in pictures, it's none other than this tensor network contraction there. So that's how you calculate your products. And now I'm just going to declare that it works for all sufficiently nice tessellations. By sufficiently nice, I mean that the cutoffs, that growing a cutoff is an isometry. That's not always true for a tessellation of the prime gray disk. So some tessellations are bad. When you grow a cutoff, they're not related by an isometry. What's an example? So I think if you tessellate by triangles, yeah, the 237 tessellation is a bad one. But this is a good one. All right, that's the kinematics done. I have hereby introduced a space which I've declared to be associated with a continuum limit of the holographic state. Let's explore this space a bit before we get to the dynamics. So how much time do I actually have?
Normally have until 5:30.
All right.
It should be all right.
Good. I want to explore some special states inside this space to give you some intuition for what these states look like. I'm going to introduce some terminology that might be in my testing with discussions with other people. This has turned out to be a controversial choice of terminology. We'll see how it goes. So remember this tessellation with distinguished oriented edge E? Well, I'm going to call the state phi gamma. I'm going to say that it has geometry tau E, tessellation with distinguished oriented edge E, if when you look under the hood, you see that it's a contraction of just V's associated with these triangles. Now phi might not have looked like that under the hood. It could have been any old state. It's like C to the D tensor C to the D tensor C to the D blah 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 blah. But I will say that that particular state has geometry tau E if it is the contraction of these tensors under the hood. And because this state really should be thought of as a UV inside H of hat as a UV completion, you just complete out all the way to infinity with these V's.
Can you say the difference between the state that has the red edge and the state that doesn't have the red edge?
There is no difference at this point. In fact, this red edge becomes much more important when I talk about the other tessellations, because then it tells us how these cutoffs should be compared. At the moment, the red edge is just superfluous information. Now, a state might have a different geometry, right? It might be that when you look under the hood, you didn't see that tessellation, so a different one, where you've done a Pachman flip through a quadrilateral. So that state has atomic geometry tau prime E prime. And of course, we're talking about a semi-continuous limit. This state lives. It's just, you should think of it really as the UV completion of that thing. So let's introduce a definition. Let's see if you like it or hate it. A state in this semi-continuous limit Hilbert space has geometry tau e if it's the contraction of that holographic tensor network for a given tessellation tau e. Yep.
I'm sorry, what are the bulk degrees of freedom?
There are no bulk degrees of freedom yet. I'm only doing the world's most trivial holographic state, not holographic code. I hereby argue by authority that it will work for the case where you have bulk layers. Now, let's point out something really interesting. States with geometry, that's not a subspace. It's a subset. So here's the warning. The subset G of states with geometry is not a linear space. You can't take a superposition of two states with geometry and get a state with geometry necessarily. And I would encourage you to think of this subset G are the states with geometry as kind of semi-classical states at the bottom. I'm going to really encourage that association. All right, we've done the kinematics, done. Let's get into the dynamics. This is the good stuff. And I'm just going to talk about the boundary. There is no bulk degrees of freedom. What does it mean, dynamics? Well, I'm going to take a pretty hardcore view here and say that dynamics means, well, none other than a complete unitary or projective unitary representation of the Poincare group, or let's say the conformal group, which is what we're aiming for here. I mean, whatever theory you have, if it's Poincare invariant, then Wigner's theorem tells us that those Lorentz transformations, these Poincare transformations, they ought to be unitaries. So I think it's reasonable to at least shoot for the moon and try and get a unitary representation of these groups. And in our particularly simple case that we're dealing with here, the conformal group has a definition. It's this plus the union, the orientation reversing part, but let's forget that. This is the conformal group in 1 plus 1 dimensions. It's just the product of div plus S1 cross div plus S1. What is div plus S1? It's just the set of differentiable functions from the circle to the circle. And as is traditional, we just focus on the chiral half. That's sort of, that's where all the difficulty is, sort of. I mean, let's focus on the chiral bit. And how do these conformal transformations act on ADS3? Well, you just take some regular grid of events on the boundary. Here's ADS3 in sausage coordinates. And then these transformations act. Here's an example of a map from the circle to the circle. Nice and differentiable, orientation preserving. And 1 is identified with 0. And these transformations act on the boundary by just deforming the events along light rays. Now, the dream, right, would be, let's find a unitary representation of the conformal group on the semi-classical, the semi-continuous limit. Let's just go for the big one. Can we do this? And the answer is no. The structure of these tessellations is incompatible with div plus S1. So if you take your favorite differentiable mapping of the boundary of the Poincare disk to the Poincare disk, is a Möbius transformation for your viewing pleasure, that is incompatible in general with these tessellations I've introduced. It takes a nice ideal regular type tessellation like this to something that's moved, right? Some triangles move a bit over here, whatever. It's not the same tessellation after the transformation. And so here, I would have been willing to give up. But it turns out that you ask the holographic state, what does it give you? Well, it gives you something else, and it gives you something really fascinating. It gives you a representation not of the conformal group, but of another group, a very magical and mysterious group called the Thompson's group T. And I'm going to tell you about this group now. And the Thompson's group T is really somehow a discrete analog of the conformal group. So there's lots of literature on this group. I'm only going to tell you one definition. There's multiple definitions and representations out there.
Discrete subgroup of the conformal group?
It's not a subgroup. And that's what the first interesting fact is.
Yeah.
Thompson's group T is that group generated by piecewise linear maps from the circle to the circle with gradient, which is a power of 2, and breakpoints at dyadic rationals. So that's a total mouthful. Another way of defining Thompson's group T is you take these 3 piecewise linear maps, compose them, add in the inverses, you have as yourself a finitely generated group. It's an infinite group. And why? Yep.
What define these 3 maps? You put the line that's like a
So the map is this dark black line here.
Yeah.
And it acts on the circle by taking, say, this point here
Yeah.
to there.
Yeah, but are you choose? Do you mean you choose this point, this key point at particular?
Yes, these kinked points have to be at dyadic rationals. At rationals that at numbers which are at some integer over a power of 2. Yeah.
So the conformal group is complex, right? And this is real.
This is real. But okay, so I was looking at diff plus S1. Yeah, and so this is real. There is an analogy. It's not
So how big is this group?
big. It's
This
huge.
is not the group of tree.
It's the group of rewritings of trees.
Yeah, it's the chaotic numbers.
It's not the p-adics.
No.
It's not.
No, it's not.
Infinite product.
Yeah,
No,
it's
Are all those piecewise continuous, meaning that C, even though it's got to jump, it's still, because it hits the boundaries, it's continuous?
yeah.
I know. I know, this describes the whole thing. Right, that doesn't have to come with chaotic numbers.
No, so these act on. Yeah, it's tempting to think that they're the same thing, but let me explain why I think this group is not. Well, I'm not going to directly answer you.
Okay.
Yeah. I'm going to explain why I think it's more like the conformal group.
Did you say it's the same thing as the full isometry group of the infinite tree? That
It's nearly that. Yeah. I don't want to say that. No, I don't believe that's actually true.
Which contains a piece which looks very much like
Yeah. So why would we care about this group? Well, because of this proposition, which is well known, meaning that I had to prove it myself, because you can't find proof anywhere in the math literature. So how does it work? You take your favorite diffeomorphism, and then it turns out there exists a sequence of elements in this Thompson group which better and better approximate that piece, that beautiful differentiable function there. Warning, no element in the sequence is differentiable. So even though Thompson's group T can arbitrarily well approximate in the compact open topology any such function, the diffeomorphisms don't belong to Thompson's group. And Thompson's group doesn't belong to the diffeomorphisms. They're really just different things. It's conjugated to, but that's a different story. Yep.
Sorry, but the thing on the left can have slope more than 2 in the elements.
Yeah. You can have power of 2 slope.
Oh,
So you know, a half is allowed, a quarter is allowed, 2 is allowed, 8 is allowed. Now, it turns out that this was a very fashionable subject, you know, about 20 years ago, when Rob Penner introduced the universal tightener space, which I still don't know what that is, but it's very elementary. It turns out this Thompson group is compatible with these tessellations that I introduced here, and here's how it acts, right? It takes this tessellation here, you act on it on the boundary with, say, this Thompson group element here, and it moves. It's sort of an interesting thing to try to work it out. It moves, say, this distinguished oriented edge to a different location here. That's how it works. And then this other element works by doing a patchwork flip there. And this element here just happens to move the distinguished oriented edge down there. Now, there's a theorem. You can put a box on it if you want. There's Thompson's group T is isomorphic to the group of Pachner flips, not the stellations, but the flips on this tessellation with some distinguished oriented edge. So you take some quadrilateral and then you flip it like that. Turns out Thompson's group T is just those isomorphic to these set of actions on a tessellation. Now, here's the kind of breaking news. It turns out you can get unitary representations of this group, and so these unitary representations are what I want to call the dynamics for the holographic state in this particular case here. And how do you do it? Well, you do it by sort of like the most obvious thing to a tensor network person like myself. You just stick the tensors in before, and you stick the tensors in afterwards, and then you say, that's how a Thompson group element acts. And you then hope that it's unitary. And it's an amazing result of Vaughan-Jones that indeed it is. So if you stick the tensors in like that, you do get a unitary representation of these maps. So for example, if you start off with our favorite vacuum state here, omega, you act on it with one of these Thompson group elements here, executing a Pachner flip, that gives you some new state, right? I've stuck the tensors in both left and right hand side. You get a state on the left, a state on the right. And then you say, well, maybe, just maybe, that defines some unitary operator on the original state. And indeed it does, but
John's result works for which V's?
for which V's?
For which tensors?
Any perfect tensor.
Any perfect.
Yeah. Yeah, it's true and quite
But we want to define this action on any state, right? We should be able to treat other states on one.
Yes, and it also works for those as well. But that's a more complicated story that I want to avoid. So to explain that unitary representation in the final minutes, let's note firstly a corroborate. Okay, if you believe me that this really is an honest operator on a Hilbert space, then what's the geometry associated to a state where we do a Thompson group element on a vacuum state? Well, the answer is it's a state with geometry given by by construction, by the tessellation coming from Thompson's group acting on the boundary. Okay, that was kind of trivial. And so we're going to have to build, how do we build a unitary representation? Well, the one that we're going to start with is we start with a subspace now, and it's a subspace called V, and it's spanned by all states with geometry G. So remember, states with geometry don't form a linear space, but their span certainly does, right? And then it turns out that this subspace of our semi-continuous limit, which you might call the space of semi-classical states and the superpositions, does give us a unitary representation of this Thompson's group T, and it acts just like you would hope it would act.
Sorry, I didn't understand why superpositions of the geometry do not give you all states in the Hilbert space.
They do. In the semi-continuous limit. That's not obvious to me. It depends on the structure of the tensor V. So if the tensor V was too trivial, then I don't see any particular compelling reason why.
Well, I thought all the states in your Hilbert space are defined by, you first take this
No, they're defined by states in boundary Hilbert spaces with a finite boundary, but inside those Hilbert spaces, the states themselves do not need to come from interactions of tensor networks. Yeah. I might come back to that. So it turns out that this action really does give you a bona fide unitary representation of Thompson's group T. So I really want to advertise this result because I think this has a very beautiful interpretation for the holographic state. It says that we can give the holographic state some kind of dynamics which is analogous to but not the same as a conformal group dynamics. It has all kinds of transformations that look like local conformal transformations and they act unitarily on this Hilbert space. But it's not a conformal filter. I mean, it's something else.
Do you have a state that is invariant of the dynamics?
Sadly, only for trivial examples. So that's one problem. There are so many problems with this story, and one of them is that this vacuum state is actually not invariant, not even under the analogies of global Möbius transformations. So that's sort of awkward, and it means it's not a ground state, right?
And why is it subgroup of the conformal group?
It's not a subgroup of the conformal group, yeah. Because the conformal group is defined to be a set of differentiable functions. Thompson's group is a set of piecewise linear functions which are not differentiable. So that's sort of difficult to overcome. But it's maybe in the transitive completion or something. Yep.
I think you have said that one treats the vacuum state, and why do you call it vacuum state?
Why do I call it vacuum state?
It's just one of those geometries, right?
Yeah, it's just one of those geometries.
Why do you arbitrarily call it the vacuum?
Because I like it. And I have no right to call it a vacuum state. Now, this was a conference on complexity of black holes. I'm going to, I published papers on Hamiltonian complexity, so I'm going to hereby not talk about complexity and talk about black holes. So, black holes, what are they? Well, I mean, there's very special black holes in ADS, these BTZ black holes, and it turns out we can generalize all this story to spacetimes of these BTZ geometries. So, this is the holographic state. The vacuum state, right? Now, how do you build a BTZ black hole when you take some discrete subgroup acting on the Poincare disk and you mod out and you look at the fundamental region? So that's what a BTZ black hole spacetime looks like in the language of the tessellations I've introduced here. And mod out means contract, right? Let's contract like that. So what's the state now? What do we get when we do this? Well, we get something remarkable. we get two copies of that Hilbert space. We get a semi-continuous limit Hilbert space right down here, and we get one up here. Of course, this is absolutely no surprise to you guys. And this object, this tensor network here, is a state inside this tensor product of these two semi-continuous limit Hilbert spaces. And what kind of state is it? Well, it's entangled. So you've got two interpretations here, right? This same state has two incarnations. It's exactly the same thing. It's either, you can think of it as an entangled state having no geometry, right? Because entangled means superposition of these Thompson CFTs. Or if you choose, you should also be able to, if you can, just think of it as a state with geometry, but it's a different geometry, right? So this is precisely this EI equals EPR. So this whole this Hilbert space really gives that structure to you, or confirms the structure. And for those of you who like category theory, you get a lot more. You get unitary representation of a group point tensor category, and whose objects are tessellations of Riemann surfaces and whose morphisms of cobordisms. Let's just skip over that. So here's the end of the talk. I have a table. And in it, I want to talk, summarize the things I've talked about in this talk. There's plenty more entries to this table. I'd love to add an entry with the word complex, wormhole and complexity on the right-hand side. I still don't quite know what to do about that. But here's what I talked about in this talk. So in the continuum, we have a thing called the Poincare disk, which is a slice of ADS3. And in the discretium, we have this tessellation of Poincare disk. Now we have on the continuum the dynamics of the boundary is the conformal group. And in the discretium, it's probably, we should call it, we use the Cartesian product of T with itself. What about the boundary Hilbert space? Well, in the discretium, I proposed it's H hat. I didn't actually, it's a bit naughty. The Hilbert space of bulk states, the bulk Hilbert space is embedded isometrically into the boundary Hilbert space. That's sort of, I guess you can, that's my argument for why that's the case. And in the continuum, so it's sort of important to point out that these Pachner flips are not small diffeomorphisms. They're gigantic diffeomorphisms. They're large diffeomorphisms where each of these triangles, which is like universe as large as a chunk of the universe, gets flipped.
Yeah, it's just, if you take the tree picture, it's just flipping.
It's just flipping, in the tree picture.
So it sounds like the p-adic groups is a subgroup of this, or which one is it?
This is a group on the p-adic numbers, I believe.
No, it's not on the p-adic numbers. So you're talking about the group SL2P.
No, that's a small piece of the group.
Yeah.
Yeah, that's a small piece that looks like a conformal.
Yes.
But
So this is these p-adic groups.
any group that acts on the tree will act on the p-adic numbers.
I will have to check
P-adic
that.
numbers are just the limits of the.
Now I knew this question came up, and I had an
That's
answer.
not important.
Yeah. I had an answer ready
I'm
for
trying
it
to tell you to
now.
read my paper.
I will do. So there's plenty more I could talk about. I didn't talk about primary fields. It turns out they have analogs over here on this side. And I didn't talk about fusion rules. It turns out they also have analogs over here on this side. And there's one other thing that I want to advertise, right? I did it all for the trees, and you're right to be kind of like, this tree. All parts of this dictionary will carry over to the tessellations, these hyperbolic tessellations that John and Dan and Fernando and Benny considered in their paper. So there's going to be this story is sort of like the first part of a bigger structure that these holographic states will I hope uncover. That's it. Thank you very much.
So general tessellation is not a tree.
Yes.
It's not. It's not all the deformations are correspond to some.
That's
You
correct.
mentioned some for some tessellation as well. But even for good tessellation, it's not all the deformations.
Yeah, you have to throw out.
There's some convex.
Yeah, the convex regions become the cutoffs that you allow, and then the local diffeomorphisms have to come from the Coxeter group of the tessellation, and so you have to be a bit careful with the elements of this table.
So related to the category theory thing, I didn't understand why it's all converted to this some tessellation.
Yeah, it's a very general thing. I just don't want to answer that question. It'll take a very long time.
So is the situation would be different for holographic code and wall flags?
With wall flags, there's a big, many of this stuff will carry over. I believe you get a thing called an intertwiner between two groups. I haven't checked that properly yet.
Just one comment about, so we have these tessellations. So in principle, we can put any tensor to give us some state. But we expect that only very special tensors will give us any state.
Exactly, yes.
That have good continuously many.
Indeed, yeah. And so what I didn't mention is a no-go theorem about tensors. So if you take a sort of generic perfect tensor, then there's a no-go theorem that Vaughan recently proved that shows that sort of the most obvious map that should be continuous is that sort of rotate by a little map, right? So this ought to be continuous. It ought to act in a continuous way. Turns out it's discontinuous for generic tensors. So the tensors have to be very, very special.
Sorry, what's it?
So you can, the Thompson group contains every rotation by 1 over a power of 2. So you can do sort of exponentially small rotations. And so this action is just not continuous if you put in your favorite, a generic tensor. But if you put in something, say, from the OPE coefficients from a CFT, then, well, we haven't quite got finished with proving, but I do believe it's continuous. Yep.
Supposing I want to sort of try to think about this as a discretization of, the bulk
Yes.
space-time. What would you do if the bulk was not doing this?
What would I do then? I would hope that there were regular tessellations that I could find on Wikipedia. So yeah, I would try and define a regular tessellation, which you can do with Coxeter groups, and you need flips, and that's more.
What does it mean to have a regular tessellation of a space that doesn't have any symmetries? Is that a well-defined thing?
I don't
The
think
generic state won't have any symmetries. So I mean, that's one of the weird things here. Is that most of the states in the Hilbert space, they shouldn't, symmetry shouldn't act very.
Yeah, so I don't know the answer to that question. I don't even sort of have a physical intuition there.
Well, the symmetry is an asymptotic property, right?
Yeah.
So it's a property of the asymptotics, which normally will go to something uniform, and then you can act with this.
Yeah, but I don't think that means that there's a tiling of the geometry in the excited state that somehow better respects the symmetry or something. I don't know.
I can't answer that question.
So is there a characterizing way? Is there a way to characterize the tensors that's
Well, there's a trivial way. So if they satisfy associativity, which that B that I introduced doesn't, then it's certainly continuous, but it's boring. It's matrix product state. So, like, while I'm answering, I'll just zoom backwards in time. So,
I think the question is whether
can you characterize the good ones?
Well, if
Yeah.
it would be a method for solving CFD.
Yes, it's pretty heady stuff. I mean, the reason Vaughan introduced this unitary action is he wanted us to build CFTs from subfactors, because there is a subfactor called the Hilbert subfactor, which should correspond to a CFT that no one's ever constructed. And he's looking for the magical tensor that will do the job. So yeah, I mean, if you got a tensor that does give you this nice action, then it builds a CFT. This one doesn't. So this one, there is a trivial tensor that does the job, right? Anyone that satisfies this equals this will give rise to a continuous representation, but it's boring. It's a matrix product.
Should I still think of all of these patches as ADS scale patches?
Yes. Yeah. Each of these triangles is huge.
Do you know if there's any connections that cluster algebras, the symbols of those are related to these edge flips on triangulations in finite
So I guess I have to say no because I don't know what cluster algebras are. So I can look up and then answer your question.
They were by Conformal.
Yeah, if you can send that to me. Yeah, I'm acutely aware I'm keeping everyone from dinner. So.
All right. Well, thank you, Tobias.